so I want to show you a little demonstration of different kinds of sediment as it relates to their porosity and kind of infer something about their permeability, the ability for water to flow through these different types of materials. And we can also look at their infiltration rate, and then we could test these possibly for the specific yield and specific retention as it might relate to preventing groundwater contamination from spreading through an aquifer and through the watershed. So I have a couple different sediments that you would could typically find underground. I have some gravel here, some kind of a medium gravel. It is well sorted, fairly well sorted. They're pretty much all the same size. This is a medium grained sand, also well sorted. All sand grains are the same size, and based on its color, I would say most likely the same composition. This is bentonite clay, also well sorted, all the same size. And our one kind of different one is a mixture of the gravel, the sand, other types of sand, and some of the clay as well. So whereas these are well sorted, all the material is the same material, the same size material. This is made of, this mix is all different size or grain size sediment material. What I want to do is pour some water. There's about 100 milliliters of sediment in each of my beakers. I'm going to start with 100 milliliters of water, and I want to pour enough water in so that the water reaches the 100 milliliter level, and that will get us an idea of how much pore space is in our sediment. And from there we can easily calculate porosity, which is going to be the volume of water that is in those pore spaces divided by the volume of the sediment, which we're going to say is 100, and that keeps it easy for the math. And we're starting with 100 milliliters of water, so the subtraction becomes easier. So I'm going to start with the gravel, and I'm going to pour some of the water from my graduated cylinder in there. You can see how quickly the water just percolates in, infiltrates in. That gives us an idea that this medium gravel, this medium well-sorted gravel, is not just porous, but it is very permeable. Those pore spaces are big, they are well connected. I think I might need just a touch more. I might overdo it here, about there. And it showing us we used about 50 milliliters of water. So if there's 50 milliliters of water over 100 milliliters of sediment, gives us an idea that the porosity is about 50% there. Let's try this well-sorted medium sand. Again, 100 mils of the sand, and starting with 100 mils of water. I'm going to pour that in just like I did. Let's observe how quickly the water infiltrates and percolates through the sand. Again, that'll give us an idea of the permeability of the sand. We want to see that sand kind of color so that we know it's completely saturated, and it is percolating down. It's not as quick as the gravel, but it is certainly moved through very rapidly. And let me just turn that around to see. Might need just a smidge more. Some of that needs to be, yeah, just a little bit more. And there we go. Nope, I didn't quite get there, sorry. I thought I had it all. This side is, there's still some, there isn't. Nope, just a little bit more. There we go. Oh, it's a little pooling on top. And yeah, I could probably pour about 1 or 2 milliliters back. I just kind of overdid it at the end there. Let me do that. I'm going to keep this honest here, Dr. Criswell, who is filming this for me. So I have 100 mils of sediment, and about, again, 50 milliliters of water was used. Again, the porosity of the sand, the medium sand and the medium gravel is about the same. The pore spaces in the sand are smaller. It took a little longer for that water to percolate, infiltrate down, but it's still the same level of pore space, the amount of pore space. So about 50 mils of water in 100 mils of sediment. 50 over 100 is 50%. It tells us something that well-sorted sediment, or if a rock were well-sorted sandstone or well-sorted siltstone, its porosity would be the same, although these are sediment, whereas if this were a sandstone, the porosity would go down because the sand grains would be cemented together and some of that pore space would be closed off due to the cement that is holding the sand grains together. Let's try this clay. This is called bentonite clay. Same thing, about 100 mils of the sediment and 100 mils of water. Let's observe what happens here. And that's just pooling up on top. It also expanded. It tells us something about bentonite as a clay. It's a clay that likes to absorb water, so it does have industrial uses. But you can see, if Dr. Criswell can videotape that, it is moving very slowly, and it's going to take forever and a day. I'm exaggerating, but it's going to take quite a long time for that water to stop being pooled on top before I can continue pouring water into this, and we can just let that sit. Ultimately, if we came back 24 hours from now, we could get some more and would be able to get some more water in that clay. It turns out we would probably get about the same amount that we got in the sand as we did in the gravel. There's just as much pore space in this fine clay as there is in the sand, as there is in the gravel, and that's because it is well sorted. So even though the grain size is smaller, the clay is smaller, there is still an equal amount of pore space, but the permeability greatly decreased because those pore spaces are not well connected, because clay tends to be very flat, platy, and sits on each other in layers like this, flat layers, and so some of those pore spaces are cut off from each other, and so the permeability, the infiltration rate, is going to be significantly slower. Let's try this mixture of everything here and see where that gets us. So again, about 100 mils of sediment, and I'm starting with 100 milliliters of water. You can see it is infiltrating, it's percolating through, it's taking its time. It is clearly not saturated. It pools up on top before, and it just eventually ultimately takes its time to percolate down. So it's actually going quicker than the pure silty clay, not as quickly as the sand, and certainly nowhere near as quickly as the gravel. So this is going to take some time, probably too long for video purposes, but we can see that this is going to take its time, and I'm just going to pour that on there. I am sure I will not be able to use 50 milliliters of water in here for this to get saturated, and that's because it is a poorly sorted mixture of sediment. There is gravel in here, there is sand, there is clay, there's some soil in here, there's all different kinds, size gravel, and there's different kinds of sand. It's not just the medium well-sorted sand here. I got some coarse sand and some finer sand, so there's a whole range of sediment sizes in here that start filling in the smaller pore spaces, and those pore spaces are filled in by even smaller sediment, so the pore space has decreased, and the access from one pore space to another has decreased. So not only is the porosity going to be lower, but the permeability is going to be lower as well. So sorting is a big control over the porosity and permeability. Grain size definitely affects permeability or infiltration, and that can, whether we want to actually install a well in a layer of clay or its rock equivalent like shale, may not be the best choice. We might look for rocks like sandstone or all gravel or loose sediment, but sandstone and another rock, sedimentary rock like limestone, would be a very good rock to drill your well into for getting plenty of water to flow into your well. The sand and sandstone typically have higher porosity and higher permeability, and those are the characteristics we want for an aquifer if we want to drill a well into there and access the water for potable uses.